Most engineering students excel at learning college theory, but put them in front of real-world industry equipment and they freeze. Technical interviews frequently pivot from textbooks to the plant floor, and candidates who haven't seen this hardware in action often struggle to bridge that gap. Today, we are looking directly at the critical communication link between field sensors and the PLC, or programmable logic controller. Understanding how these specific components actually talk to each other is step one to becoming industry-ready. In industrial automation, sensors send signals to the PLC within a highly specific range, 4 to 20 milliamperes. But why rely on current? Why doesn't the industry just use a simple 0 to 10 voltage signal instead? And if we must use current, why start at an arbitrary 4 milliamperes rather than a clean 0? Memorizing the 4 to 20 milliampere rule is easy. Knowing exactly why it exists is how you pass advanced automation interviews. Let's start with the first concept, comparing voltage transmission against current transmission over long distances. In massive industrial plants, signals travel through hundreds of meters of cabling. Voltage signals suffer voltage drop, losing strength over distance and giving the PLC inaccurate readings. Current signals, however, are unaffected by this resistance, reaching the controller in their exact original shape. Current is chosen over voltage because it guarantees the controller receives the exact data the sensor sent, regardless of the plant size. This leads to the next logical question. If current is the best method, why not use a simple 0 to 20 milliampere scale? This diagram shows a 0 to 20 milliampere system. An empty pipeline naturally outputs a flat 0 milliampere signal. If the physical wire breaks, the signal drops to 0. The PLC receives the exact same reading, leaving it totally blind to the physical damage. Using the 4 to 20 milliampere system, the empty pipe outputs a baseline 4 milliampere signal. When the wire breaks, that steady flow instantly drops to 0. Because the PLC expects 4 milliamperes, a 0 reading instantly triggers a warning alarm. In the industry, this built-in safety feature is formally called a live 0. Live 0 fault detection is brilliant, but it is actually only the secondary reason for the 4 to 20 milliampere standard. The primary, most crucial reason the global industry relies on this standard is loop power. Digital displays and transmitters require constant electrical power just to turn on and operate. Look at this field transmitter cross-section. That constant 4 milliampere baseline perfectly powers the internal electronics. This eliminates separate power cables, letting you route both incoming power and the outgoing signal over a single simple 2-wire system. On a facility-wide scale, cutting the wiring requirements in half saves millions of dollars in copper and plant construction costs. By combining signal integrity, fault detection, and power delivery in a single loop, 4 to 20 milliamperes became the global industry baseline. To recap, first, current prevents voltage drop over long distances. Second, the 4 milliampere baseline creates a live 0 for immediate wire break detection. This checklist highlights our third point. Loop power allows for highly efficient, cost-saving 2-wire setups. Explaining these three concepts clearly is what separates a classroom education from the demands of a working plant. This is exactly the knowledge demanded by high-value roles, like PLC programmers and maintenance engineers. Mastering industrial reality over textbook theory is the fastest way to increase your employability. Stop relying purely on theory and take the next step toward becoming industry-ready. Visit coach.manmeetsinghbhatti.com to register for our comprehensive free webinar. Seats for this session are strictly limited. Learn the essential practical skills, master the real-world equipment, and confidently step into your new industrial automation career.